So,
Yeah.
we can say that GPU programming has been around for a relatively short amount of time. So we don't have now most of the supercomputers, they get their performance from using GPUs, but this was not the case a few years ago. And like this is why I think there is lots of very good codes around, and they are they have been used and they got good results. But of course, we always hit a limit, and they are just CPUs. And it's something that now happens in many computing center when we have lots of groups that want to use for example, Lumi, to take advantage of the GPUs on Lumi, and then they don't know how, and they ask us to help them. So we have to take the CPU codes and then port them to GPU. So this is not a trivial task. So we saw that running the execution model of the GPUs is different from the CPUs, and we have to think in different ways. So here are a few steps that need to be followed and, to actually get the code working on the GPU. So first, we have to look for the so-called hotspots, identify the code that the program spends most of the time. We have this observational principle that says that about 10-20% of the codes accounts for most of the execution time, most of the execution time of the program. These parts we can do them by having some fancy profiling tool, which will tell exactly how much time is spent in each function. But also, in this case, it's okay to just go there and put on the CPU version, have some correct use the correct function, measure the time, how much time is spent in each step, and then go and decide, and then go and start identify the code which actually needs to be coded, to be ported. We should never reinvent the wheel. Lots of mathematical libraries have equivalent on the GPUs. So all this linear algebra, fast Fourier transforms, generating random numbers, machine learning, they all have some equivalent on that we just have to plug in our data and then call it, and it will be very fast. And this is the happiest case that we can think about then, because that's minimum amount of work. But it's not always the case. There are always going to be some loops that the code spends lots of time, and we have to address them. These, in general, when you have a CPU code, it's people write, the scientists and the programmers write these codes with the thinking of the CPU performance. So they do some small optimizations, and often the loop might not even look like it's parallelizable. There are some small dependencies. So it's quite normal to have to actually, before going from CPU to GPU, to take the CPU loop and then start to rearrange it a little bit. Change the order of, if you have nested loops, maybe you have to change a little bit the order of the loops. And also, if we have, I saw at least in the program that I'm working with, I saw that there is like these loops that do lots of calculation inside the loop. And for the GPU, we don't just take one big loop and put it on the GPU, because having too much operation inside a kernel is not beneficial. It's using too many of these registers, and also it's maybe, for my opinion, it's more difficult to read the code. And sometimes also part of the loop might read different parallelization. So we would have to we take the loops, we rearrange them a little bit, and then we split them as much as we can. And finally, now that, I mean, you start to porting, and then we get some kind of we get working version. We know it's correct, and now we can start to look at the performance. We can check what optimization we can do, and of course, I think that the biggest optimization that one can do to a GPU code is the memory, improving the memory access, and trying to use shared memory, and also trying to ensure that the resources of the GPUs are used in such a way that at all time all GPU can be it's busy doing calculations. So it's like, let's say, we haven't talked about this, but like something called high occupancy, as high as possible. Keep the GPU busy with GPU threads running on them. And I have here a small piece of code. So it's one of this complicated, one of the loops that from a real application that I was working on and tried to port. So it's just 2 pages. And in this application, we have insights. So it's a set of particles which interact with each other, and there is like a short range interactions, and then each particle has some neighbors, and all the computation that happens corresponding to this to compute the force that is on this one side with index I is happening with these neighbors. And okay, you see this loop is done, let's say, in a serial manner. So the programmer chose to define this index K2 in this manner, which is like built recursively. So this is like a small it's like a small dependency, but I mean, this is something that is easy to get rid. What else do we have here? So first step of the loop, for each pair ij, which gives index K2, we see that we have these 4 nested loops. And actually, here, when you look at what actually do with nested loops, it's actually a summation. So we for each pair ij, for each index K2, we have these 4 loops which are just adding something from some other variables. Now, when this part of the loop is finished, now for the same K2, it's trying to do some normalization. So here, this is okay. It's dividing with there is a normalization factor for each particle, which is given from somewhere. It's known from before, but now here we have something called like a dot product. So for each particle K2, we need to compute this dot product. And then after that, of course, if this dot product is known, this part, the rest of this calculation is very simple. It's more or less the same operation for each component of this, for each element of this matrix. And now once this is finished, we have another last step. First, we have this operation, which involves only the K2 variables, but then we see that for the atom itself, so when this index j is equal to 1, we actually have another summation, and so we need to know this array before so that we can actually just add it to this to the elements corresponding to this variable k3. So one thing that is important here to know is that you see this variable that we are trying to compute, we are two-dimensional, and this k2, this can be as big as let's say 10,000 or 10,000 times 20. Well, it can be more. So this is the number of pairs. But this fast-moving index, which here is counter, this fast-moving index is something in general. You see that here it's again the same variable, and we have it's 1-to-n slope, and we know that this is 100. So now, of course, I mean, one thing that I want to do a general code, but in this case, I know that for all my cases, I have a situation. It's a two-dimensional matrix. I have this index, which is the slow. I'm not sure how to spell this, but okay. So this index, it's very large. There are lots of particles. So we want to reach millions maybe at some point, but it's at least 10,000, and then we have the other index, which is between 1 to 100. It can be up to 500, but still, and that gives us some indication that okay, in the code we know that one block is between 1 and 1,000, so we can use this information for when we write our code. But okay, first step is that in order to rewrite rearrange this loop, we need to just get rid of this false dependency. So it's what I do here is that I construct a list of indices, and then I replace these two loops with just one loop. So now k2 goes from 1 to k2 max, and from time to time I also need this variable I, but now I have a list of these indices, and I can retrieve it. And building this list, it's actually very fast, and I can also do it on the CPU, and I can at the end, when the code is like finished and we have everything ported, I can incorporate building this list with them, computing the neighbors, because we are looping from all the particles. And now, as I said, we saw that this is quite a long loop, and we can say that there are 3 parts of this loop. But if I would have a kernel which does everything, then there are so many variables there that it's possible that these threads, the CUDA threads, will use too much registers, and when we use too much registers, then it will decrease the amount of threads that can be active in the same time. So you result in something in a small occupancy. So even if having more kernels would mean that we have to save some data to the global memory and vary it again, the fact that we can use all the GPUs at all time can be beneficial. The other reason to split the loops is that we could use different, we could parallelize a little bit different each part of the loop. So we don't have to do the parallelization here all the time over this index k2. Depends on how the memory access is done, depends what's happening inside, what's happening. And so we can take advantage of that. Also, other thing is that here, in the last part of these calculations, you see that in order to compute this line, I have to know this line. So in order to compute the k3, I have to know all the values of these variables that happens for a specific pair, or specific particle. So for all the neighbors of a specific particle I need to know all these variables. And if different threads are computing this this variable corresponding to K2, when they reach, when it's not guarantee that the thread that computes this corresponding to K3 will read the actual value of this variable from the memory. So because we don't know what order things happens in the GPU, we cannot import a specific order. So at least these two parts, this part here, this one has to actually be splitted into. And also here, for example, we have to compute this kind of dot product, and also this in a way similar. It's if we just parallelize over K2, this will not necessarily, this won't be so trivial to do it. So let's see. Okay, so well, my approach here is that, okay, I split the loop in 3 parts. So this first part of the loop, so I just write it like this. So I have the outside loop, which goes from 1 to the maximum number of these pairs, and then I have this inner loop here that does some calculation. So now, I mean, here we can write a kernel, or we can just throw in an OpenMP directive or OpenACC and then parallelize over the K2. But there is an issue here with these memory accesses. So for example, if we do that, now this inner loop will actually result in uncoalesced memory accesses, because let's assume that we have 2 threads computing something for K2 and K2 plus 1. And then we have the counter, which goes from 0, from 1, or to, yes, from 1, all the way to some value, which is about 100. So the thread that has index K2, then it will access some memory, but then another thread with index K2 plus 1 will access memory, which is far away in the memory, which is far away by the size of this dimension. So this is very uncoalesced accesses. So I made here a small table. So this variable, if we have three threads, and like with some value of K2, and then let's say all of them, they reach a point and they have to, where the counter is 1, and here I put the index. So this variable that is here, this variable sobrad there, accesses, let's say, the first element of the array, but then the thread which is in the same warp and has the index plus 1, it will access something that is far away by, well, I made a mistake here, it's actually nsop, and that, but anyways, it's far away. And then also we have this kind of variable, which is in the same way, if we would parallelize over the K2, then again, the accesses will be quite far away for threads in the same warp. So this will be very slow. And we, in this case, our solution to solve this kind of uncoalesced access was actually just to transpose the data. So now, if we look at the code here, I put the first thing, I transpose the data before I enter this loop in some other way. It's only one operation, while here, if I don't transport the data, every coalesced access happens for every counter element. So that's lots of accesses here, or lots that were very slow, and our solution is that we do one transposing, which is maybe not so efficient, but then we avoid hundreds of the accesses in the same time, which are very inefficient. So now, in fact, when we do this porting, after we do this change, we actually got for this kernel a factor of minimum 10 times speed up for this specific operation. Now, Now that we did this, we rearrange our loop and we transpose the data. Now we can actually take this loop and just parallelize over the K2. And here I put an OpenMP directive, which of course is not complete, but it's just to give an idea that now this loop, in my opinion, it's ready. Now I can just write a kernel which each thread executes one value of this K2 index for each pair of particle ij, and it does this summation inside. Now, the second part of the code, so I wrote it like this. So now, of course, before going to the second part, we do another transpose, but as I said, this is still the net gain. We have a net positive gain here. Our code runs faster, even if we're doing some extra steps, because it was very slow before. So now that we get here, we take the second part. We see that first we need to compute this part, this dot product, and if I would just parallelize over K2, this would be again a loop, which is very inefficient in the memory access. But so what was option? Our solution here was to actually pre-compute this dot product, make another loop. So and then for each when going and then compute this dot product and save it to a matrix. So in this case, we have again all the loop from 1 to the maximum number of neighbors, and then for each K2 value, we have an index I, and then of course we have a loop because the dot product is actually summation over the one of the dimension. And when you save it here, and now that we have this value dot soap saved into the memory, we can now go back to our original calculation that we did there and just put it here, this matrix. And now this we see that this loop now gets a little bit more simplified. So we have 1-to-n soap and we have this K2 operation, but practically we can just apply directly on this loop some parallelization, and everything is okay if we do it over the whole. So this is also a loop practically. So we kind of collapse this outside loop to this 1-to-n soap, which is another loop. So now I'm running out of time, so sorry, I have to hurry up, pass faster. I take the second part of the loop, and we see that first we compute this dot product, and here is how we parallelize it. First, so here I put this OpenMP directives, which is OpenMP target themes distribute, and what this does is that it's going to take all the values of K2 and is going to create blocks of groups of threads, and then each of these group of threads is going to now do this operation, which is here inside of this summation. So it's for each group of threads each group of threads is going to have n SOAP operations where it's doing the summation. So formally here we have the OpenMP again. Now I have OpenMP parallel do. So that means that the next loop, this one, is distributed over all the threads, but inside the block. And because I do a reduction, I just give this hint to the compiler that I want this is a variable where I'm going to accumulate the data. So now, of course, I can also write this as a canvas, and this is what we do in our code. We wrote this ourselves, the reduction, but this also works. So and depending on compiler, is fast or slow. And now that this is finished, we see we save the dot product value into a global array and go back to the second part of the loop. Now I rewrote this loop, so I keep the outside loop the same, and when this one-to-one SOAP, it can be written also as a loop. So I do again I do again something similar what I did above. I say that each block of threads will each K2 will be assigned to like a block of threads by using this target teams distribute, and then I have also this let's say trivial operation where I now get the final result for this part of the loop. When this is done, this loop is going to be done using just the threads in one block. So and now this is all okay. I think that I'll say that all the memory accesses here are coalesced, and I might be that more performance can be obtained, but we were happy with what we had, so we stick to this this version. And finally, so we have this last part of the code. So now here, what happens is that we see that we have two lines. First, we get the K2, but then also we see that here we accumulate the value from the K of this vacuum. We add it to this index K3. And now if you distribute over the K2, now we would have K3 overall threads. But I mean, how to say, this corresponds with K3, it's just one value from time to time. So the K3 is not a variable that should be distributed over all the threads. So here, our solution was to first just do the first part. Now we obtain all the value of this for this K2. If we write it like this, then now we can again do the parallelization. It's almost trivial parallelization, but then the second part of this, which involves this K3 variable, we have another loop which goes only from 1 to n sites. Now I use the same strategy for the parallelization. So for here above, we see again that we have every block to do one value of K2, and then we have this inner loop, which is then distributed over the threads in a block. And then for this part, which involves this K3 variable, okay, it goes one from one sides. There is a typo here. And we also have this inner loop again. So again, same kind of division of the work. But here we put the I sites. Each block makes one I site. And this is also still lots of blocks. And then in each block, we do this second loop, which is 1 to n SOAP. And this n SOAP is also like between 1 and 500 or 1 to 1, between 100 and 1000 maybe. So there's enough parallels here to distribute this work to these threads in the work group or in the block. So just take home messages. So doing a porting from CPU to GPU is not trivial. So, but there's lots of work involved. So, but well, some steps that can be followed is to find the hotspots, find the parts that are worth porting. Don't focus on the pre-processing, post-processing, reading data from the disk, which are not so important. At least they're not initial stages. Try to use library when it's possible. They are very optimized and they're very fast, and they will make our life very easy. Well, loops that are written when you write a CPU code and when you optimize this code are not directly, how to say, parallelizable. You need to do there's some work to be done there. These loops have to be changed a little bit. Some operation might be rearranged. So that the final we get the loop in a shape that we can see now. Oh, now it's obvious. Now we can apply any parallelization. We can put OpenMP directives, or we can just write a kernel there, and it's going to be correct. And once we get the correct code working, then start to see what kind of parallelization, what kind of optimization I need to do. Where is check the memory access pattern. We see that when you have a multidimensional arrays, like in this case, some operations are quite efficient on the CPU, but then when you go to GPU, the memory access is there. When you do the parallelization, it's not necessarily the same. And even in this example that I show, we see that I had to do one extra step to do one transposing, and even if this is not very efficient operation because there are so many memory accesses in some part of the code that were very inefficient. Just doing memory transposing was actually gave me a net positive gain. So the code was smart running. In total, even if the transposing in my code was running 10 times faster by just doing this rearrangement. So, and now this was kind of a summary of the content. So here we can see I put here the whole loop. So there's a little bit more, not just one line, but we see there are 3 components, 3 matrices to be computed, and here also 3 and 3. And I put a refactor code, so actually we see here it's much nicer to see the refactor code and to look over it and analyze it. Compare this refactor code with the original code and see what was done differently. Okay, thanks. That's it. So next we have some other stuff for porting.
Yes. As for the second part of this episode, and the instructor entry is not available, so I think we have to skip this part, and we will continue to the next episode about the theoretical part of the recommendations. So I will talk this part. Yeah, step by step, please copy paste the link at the. Yes, thank you. So let's start right here. So we have learned a lot about the GPU programming and the variant models. For example, the directive-based models, OpenACC, OpenMP, portable or non-portable models, and for CUDA, for HIP5, and for things. And also we have some high-level language support. For example, Python, Julia. We did not mention, but I saw something quite interesting about Rust. So if you are quite familiar with this, probably you can how to handle the Rust using GPU programming. It's available. I saw one CUDA part. So like this, which one is suitable for your project if you're going to use for the GPU programming for programming and for the data analysis? So if you're going to use this for your computations, there are several factors we should consider before you choose the suitable framework for you. Number one is the portability. Why we list this one to be the number one issue is that you should make sure which GPU you're going to use or which you're going to have. Is NVIDIA GPU, AMD GPU, or the others. And then to see if the framework you're going to use is suitable for you or compatible with the GPU type you're going to use. This is a little bit necessary just to avoid some mismatch between hardware and softwares that might be limited the performance of your code. So choose the right one and use the right programming framework for your project. If you target to multi-platforms of GPU, so it's better to adopt the portable kernel-based models, because sometimes you have to switch between one platform to another one, from NVIDIA GPU to AMD GPU, so to avoid loss of programming effort. Yeah, so talk about the programming effort. The second issue should consider this aspect, which is how much you should pay to run this GPU programming. It is better to select a framework that support the programming language you are comfortable with. If you have the serial code that is written in C, C++, or Fortran, maybe a better start point is to use the directive-based models because either OpenCC or OpenMP offloading, because this is really straightforward and you just provide some directives like hash pragma things in the before the loop, and then the compilers know that okay, this loop will be executed on the GPU part. This consideration will ensure a smooth transfer from the serial code to the GPU code. It can make sure that it works and it can get some efficiency from using the GPU for programming. If you have a Python code using NumPy, Pandas for either programming or for data analysis, so maybe a good way to start to use CuPy or CuDF, means data framework. As I mentioned before, if you select, if you're going to select the PyCUDA, so you have to know more about the GPU programming things. For example, how to manage the data transfer between CPU and GPU. Before launching the kernel, you should copy the data from CPU to GPU side and then launch the kernel. And during the launch of the kernels, you should have the optimal combination of number of threads, number of blocks you're going to use, because the different combinations will have a significant effect on the performance of your code. And after you launch the kernel, you have to get the data back from GPU to CPU side. So the data transfer between CPU and GPU is kind of bottleneck thing to influence your performance, the code performance. So you have to balance this. Do I need to copy data, or I should generate the data just from the CPU GPU side and just focus on the computing? Yeah. In addition to this, it's also important to check the availability of supportive resources for the framework we choose, like document. If this have a good documentation, have a good example, tutorials. If yes, then you can follow the tutorial examples to run the code yourself first, and then gradually adapt your code to the GPU version, from the CPU version to the GPU version. If there's also a good or active community, for example, you use Python, so we have a very good community for the Python part, lots of libraries from different vendors, and so it's quite good. Then you can get kind of quick feedback from the expert if it comes to some problems. Sometimes there's no necessary for you to grab everything from scratch. You can just use available packages or libraries to speed up your computing. For example, you can use QFFT if you are going to perform faster Fourier transform. If you're going to handle the matrix multiplication, you can use available libraries, packages right there. Number 3 is what I'm going to handle is the performance requirement. How you require the performance for this project. Some framework can do a lot of things for you. For example, I mentioned like a number yesterday. So number can handle lots of things, data transfer from CPU to GPU, launch the kernel, and then take the data back from GPU to CPU. Yeah, because of this, number can do lots of things for you. The cost that the performance may be not so high as number automatically. This number can choose the procedures for this, and so if you are going to have a high performance for your project or for your code, so it's better to handle this precise manually. If this, so you have to equip yourself with good knowledge of GPU programming. I mean, for example, if you use CUDA, you might have a high performance, but you have to handle the details of data transfer and launch the kernels with the optimal combinations of number of threads and number of blocks you're going to use. so that you can achieve better performance for your code or for your project. So cost benefit analysis, this is also a factor you need to consider. If you have a good understanding of your code, you get some of this code from your boss, from your colleagues. So before you start to port to the GPU, you have to have a good understanding of this, the flow of the code, how much processing power you need, the amount of data you're going to handle, just one file or lots of files distributed somewhere at different folders in the computer, or you have to read this data from external hard drives. There's lots of loops or double loop, or lots of multiple loops in your code. If yes, how to handle these loops and how to map the data from this matrix to the GPU thread blocks. Then you can have you should have like clear information about this, and then you know where is this data and how can I get this data from the GPU cores. So in the code, you can also see if there are lots of if-else statements in your code. If yes, you have to avoid this, or you can focus on the if statement as the one block and else statement other block. So you have to balance this. Otherwise, you will get poor performance of your code, because when you launch the kernel, if you have the if-else statement during this warp, if some thread run the if statement, the other thread have to wait until the execution of the if statement is over, then they can start to run the else statement. So this is just the balance of the efficiency and also the how to choose the thread block combinations. As Chris mentioned before, that roughly if you have the code, roughly 10 to 20% of the code will cost 80% of the execution time. So how to balance this aspect, which part you are going to run on the GPU part and which part you can use the CPU to handle. This is also another cost benefit thing you should consider. I would like to also mention one thing about the memory issues, because in the GPU side, if you perform the GPU programming, you need something to know about the memory issues, global memory, local memory, and at the different how to differentiate these memories for your code. This might be another issue, but this is you need to have to know more about the GPU programming. Yeah, and these factors will help you determine the suitable and the cost-effective framework for your project. That means which framework are you going to choose depend on lots of various variables like this. I'm going to have a short summary about this. So the decision of choosing between GPU programming frameworks often depend on lots of factors. For example, what is your problem? What are you going to use the GPU programming to handle? Lots of data or lots of precise? Not so many data, or is data extensive or the precise extensive? So where to start? If you have the code, write in C or Fortran, maybe a better way to start using OpenCC, OpenMP offloading, because using some simple directives or pragmas is you can get the benefit from that. If you have a large project, you have thousands of files like this, for example, like a GROMACS, so you have to make the balance of these. In addition, the background of knowledge of a programmer might be also a issue. If you're not working on this before, we just if working on the natural science and you just use this programming to also processing some data from the computation or from the experiment, it might be that may be not necessary for you to know about what is the processor, what is the hardware thing. You can just focus on the data analysis part. read the data, process this data, and then get an output, and then use some packages for the data visualization, for example, matplotlib. And if you have a very good curve, well, you can publish these results. Maybe that's what you need to know, and do not put too much time on the hardware thing or thread block thing. That will take a lot of time, and the performance maybe just increase maybe a little bit, not so much. So the balance of cost and the benefit. So time benefit, how much time are you going to invest to learn the GPU programming? If just you want to try, you can start from what you have right now, or just from the scratch. If you want to learn systematically, learn this GPU programming, and also to build something yourself, you have a lot of ideas, and you have a lot of script, and you want to merge this script to let's say a package. Then hands on this, probably you should systematically learn one programming language, for example, Python, and especially the object-oriented programming part. So how to design lots of modules like this. And then the performance need, how much performance you're going to need. If you have the one file and you post-process the data in this file, just need like 5 seconds. If you use GPU programming, it might be increased the time for this processing maybe decreased to 4 seconds. So there's just a 20% increase. It should be okay. But if you take a lot of time on this increase, I don't think so. They take too much, because even you use the CPU programming to run this Python code in your computer, it does not take too much time. Then it is. Maybe a better way, if you have a lot of files, you can learn how to use Bash, how to find these files, and then once I know these files are there, I just copy this Python script to that directory, run this to run this Python script, and then get back. The thing you need to do is to get what you should get, either images, data, metrics. Then you're going to use this data for further applications. You should have a good balance about this aspect. We skipped some part of this, the porting between different GPU frameworks. Now I can see HM is available. HM, can you talk something about how to use Hipify to?
Yes, yeah, we can do that.
Yeah.
So I share my screen, or we can just use the
Sure.
that screen. So can you see? Can you see my screen?
Yes, that's clear.
Okay. So how much time do I have? 10, 15 minutes? More?
Half an hour, it's okay. Maximum half an hour.
Half an hour, okay.
Yeah.
I will probably be shorter than that.
Yeah. Great.
Anyway, so this part is about porting from CUDA to HIP. And of course, this is the case where your code is CUDA-based, and you are going to run on Lumi or an AMD GPU-based machine. There are some tools that are available that can be used for porting codes. For porting codes from CUDA to HIP, as far as I know, there are two tools. There's Hipify Perl and Hipify Clang. The main difference is that Hipify Perl, this is basically a very simple script. What does is simply it replaces the prefix CUDA with the prefix HIP. And that's a very simple, it's a very simple syntax. So the way you do it is there are basically 3 steps that you can follow to port from CUDA to HIP. This is a long an old syntax. So I think now there is a ROCm 6.03 that you can use, and with the Hipify Clang you can generate the script Hipify Perl. And the syntax to do that is simply you need you have the CUDA, your CUDA program. Use the syntax, the command Hipify Perl, and the output will be printed here. So the command will basically, as I said, it will simply replace the prefix CUDA with the prefix HIP. And then you compile with HipCC or or CC. So that's basically the command, the syntax of porting with the hippify Perl from CUDA to HIP. Another tool which is more robust is hippify Clang. Hippify Clang, however, it requires CUDA toolkit on AMD GPU-based machine. If you are trying to do it on Lumi, something we have tried last year, you won't be able to directly install CUDA because of some permission issue. The alternative that we tried is to use CUDA Singularity. So in the same way, you need the ROCm, and you need to export the ROCm from inside the Singularity. And the syntax here is you have the command hippify Clang that is already available on Lumi with the use of a ROCm module. So you have your code, your CUDA-based code. The output will be printed here. So what you need to define, you just simply need to define the path to CUDA. That's the path inside the container, and some include headers, obviously. So that's basically the simple. This is basically the syntax how you can port CUDA code to HIP with hippify Clang. What else? There are some examples here if you want to try. There are situations where it's difficult really to port with the hippify Clang. This is the case where you have a code that combines some machine learning based model and some kernels. So it can be a little bit challenging. And there are also situations where even directly porting codes wouldn't be 100% ensured, and then you have to do a lot of modification in the code. So this is basically for porting code with these two tools. I'm not sure if we can give you probably a few minutes if you want to run some examples, or we can go directly to porting code from OpenACC to OpenMP. Okay, I will go to cover the next part, and then you can get probably a few minutes to run the examples, these examples. You can also translate OpenACC C++ to OpenMP C++ with the compiler class. This is a compiler that has been developed by a group in US, and the key here is simply you need to build the compiler class. There is also for Fortran, it's called FLAS. I'm not sure if this tool is available on Lumi, but you can build it in a straightforward way by following the steps here. So the syntax, when it comes to the syntax, how you can compile OpenACC C++ to OpenMP C++. This is basically the syntax. What you need Clang, which is already available on, I think, on Lumi. You need to define some flags here, and you have your code, your C code here. So the output will be printed here. The scenario is really very straightforward. The only thing you need is just simply to make class available on your environment, and then simply running the syntax here. So once the code is ported to OpenMP, the second step then obviously to compile it, and you can compile it as you are compiling any OpenMP code, loading the necessary module and compile with the wrapper CC. So there is an example here that you can try. This is a very simple example that do not contain any libraries. This is probably one of the challenges that you might experience when porting codes for OpenACC to OpenMP. So I think that's probably I have covered what is necessary. I think if I'm going to summarize what I have shown you now is the porting code from CUDA to heap. There are two tools. The first tool, very simple pair-based script. It simply replaces the CUDA prefix with the heap prefix. The second tool is more robust, heap-clang. That requires some effort. You need the CUDA toolkit, and the syntax is very simple, as I have shown you. The third tool that I've shown you is porting OpenACC C++ to OpenMP C++. Once again, you simply need to make Clang available on your environment, and the syntax once again is very simple. And then once the code is OpenMP, then you can compile it, as I have shown you with the wrapper CCC. So that's what I have. So this presentation is basically supposed to be presented by Andre. He's absent. So I think you can get probably 10 minutes to run the exercises, and we are here to answer all your questions.
Let's continue, move on to the next episode. It will be the programming examples. So Stepas, give it to you.
Thanks, Yongli.
Yeah.
Okay. Welcome everyone again to the last teaching episode of this workshop. You will still have time to discuss your code and maybe any examples that you still have questions about in the afternoon session. And for the next hour, I will be talking about one specific programming example, so-called stencil computation. There is probably more material together with different examples of different programming languages than one can cover in an hour. So I invite you to either listen to me speaking, going over some things, and or in parallel maybe try already something yourself. At first I will explain the example in short and then go down to the implementations. The aim of this is to show you some different variants of programming models and programming languages implementing the same basic computational problem. What is the same, what is different, and maybe how it actually compares to each other in, for example, in terms of computational speed. So the specific implemented problem comes from the physics. If you model heat flow in some two-dimensional area, then that heat flow usually tends to go from the more heated areas to the less heated areas. This is governed by certain differential equations. And if you know how to encode those differential equations, then you can evolve your system containing some energy gradient or heat gradient in time and see how it disperses over your rectangular, or in our case, a square area. So here on the screen is a possible example of such an evolution where the starting conditions are some cold dot in the middle or cold circle in the middle of the area, and then you can have also boundary conditions, too hot and too cold. So as I mentioned, this is then in math, this is solved by solving a particular partial differential equation, and one can use numerical methods, so convert this analytical differential conversion into some numerical expressions, discretize this equation to be able to solve it. It can be done for many time steps at once, or it can be done time step after time step. So this is the case that we will be using today, and I will show the or you can look up the particular expression, some numerical expression that corresponds to the solution of this differential equation, but the main principle is that it is some average sum on every point based on the values of neighboring point. And so that gives you a new value for the energy or heat, basically function U for the next time step. So this is called stencil because what you have, you apply some template on every point on your two-dimensional grid, value template, and then get new value at the center of that. So this is called stencil, and this is actually not restricted only to physical problems or thermodynamics problems. You may have noticed such method in different kinds of computations as well. There is a short question where you can find this. So a couple of examples is convolution operation is basically equivalent to this. So you have some convolution kernel and then you do a weighted average over that kernel. Average is also this type of convolution, so you can say that this is the same. And this can be used, for example, to implement simple pooling layers in machine learning neural network chains. So once you implement such a method, you have to think about some now technical considerations. Of course, first you have to ensure that it actually accurately recreates your solution of differential equation. But after that, there are technical considerations. So can I make it fast and not just analytically correct, but also accurate in numerical terms? So here, the optional formulas for the numerical implementation of said differential equation, and also note on the fact that one cannot just make any time step. So one has to be able to accurately model this time evolution, one has to take some limited time step. And this means that there will be some work for your computation, for your executable to do. Second technical consideration would be what to do with area boundaries, because again, stencil averages over neighbors. So for boundary elements, there may be no neighbors. There are a couple of solutions. One of those is chosen and implemented there. And future question would be, let's say I do this and try it on, and it's good enough, but maybe still not good enough. So can this particular algorithm be optimized further? And I will not be talking about that today, but you will be able to think about some things you already heard throughout this workshop, for example, on memory access patterns that I won't be touching on today, or the fact that maybe it is possible to overlap the computations of multiple time steps. But for the purposes of this particular demonstration, each time step will be fully computed before going over to the next time step in the evolution. And so the example has already been implemented in a few ways. You can find those in the examples section in the teaching material. The work is ongoing to add more examples to that. For example, plain CUDA. The currently available ones are OpenMP GPU offloading using C++ as the implementation language, SYCL over C++. Then there's a Python implementation using Numba with CUDA support, unfortunately no AMD support, and Julie one. And at this point, I would like to make a short poll. So it is already there in the HackMD. Please note which of the frameworks that are available right now you are personally most interested in or or maybe you will try them in the future, or maybe you're about to try them already. I probably won't be covering Julia explicitly because I'm not the expert of it, but you're definitely welcome to try out the examples. The section is written out quite nicely, and if you end up with some problems or questions, please ask in the HackMD. My colleague instructors will, of course, help you out with this. So as you see there in the teaching material, the next 5 sections basically cover the reference implementation and the various GPU-based implementations currently available with some result. I will start from reference implementation in C++ plus thread parallel OpenMP, to be able to compare then various GPU-based versions of that. As I mentioned, the code examples are in the repository of the lesson material. If you want to try them out directly, you can download the repository or clone the repository on either your resources or resources on the cluster. Let us know if you can access the cluster, because this morning there was some incident with Lumi actually. So some things are back to work and some things are not. One thing's not working is the web interface of Lumi. So if you want to access Lumi, you have to do that through SSH at the moment. Okay, so in the terminal, you can see that a bit earlier I asked for, for an allocation to be able to try out the examples here. Hopefully, you have some way to access the resources as well. And now I'm going to the lesson material containing repository with the examples, GPU programming, content, samples, stents. As you can see, there is base implementation in C++, and there is a Python implementation, SYCL, Julia, and maybe some others in the future. If you already have cloned the repository in the earlier days, don't forget to pull any changes, because there may have been changes since the start of the workshop. Okay, so before going on and compiling and running the examples, I will briefly go over what it is actually in code, the example. So the main computational part, we will try to get to run on the CPUs or on the GPUs, and that probably takes most of the computation time in this particular problem, is this stencil update loop. So 2-dimensional grid, every point has to be updated according to some predefined formula. The formula is at the bottom, and the rest is code needed to encode this in a reasonable way. Then this eval function is being used multiple times, so for multiple time steps in the main function. And if you want to know what the default params are, you can find them in the auxiliary file. We will be focusing on this, so on this double loop, and we will see in some cases it actually ceases to be a loop, as you may remember from the kernel-based implementations, but still the aim is that the code should be recognizable regardless of what specific implementation are you using, because then this is easier to understand for other people, easier to port, and so on. So the compilation step, I'll try to recreate these on Lumi. Copying those. This is the compiler that the makefile uses. Oh, it's there. And if everything goes well, it should build in a few seconds. Also, let me know if the zoom bar covers the last few lines, then I get the terminal a bit up. But I think it should be fine at the moment. Okay, so after the build, what I've got is 3 versions of the executables. What are those? I will be telling in just a couple of minutes. They are stencil, stencil off, and stencil data. I can log in interactively to a compute node and then start the executables from there, or I can use srun driver to put that on the login node, on the compute node, and run it. And if I do that, I get something like this. Same for the other 2 versions. Okay. So now what are those? Stencil is the basic thread parallelized version, so it doesn't actually run on the GPU, it runs on the CPU, and it uses OpenMP threads as shown here. The directive, OpenMP directive, pragma-mp parallel 4 is parallelizing this loop, likely only the outer loop. You can adjust that if you want through some other keywords in the directive, but as you will see in the second, at the moment, the CPU parallelization is doing quite a nice job on smaller grid sizes. So let's check. In the table on the screen, there are some test results of the run of the basic executable. And then there's a graph, 2 graphs. So scaling based on increasing time steps, and then based on increasing computation grid size. In case of time steps, scaling looks quite nice. As you see, increasing number of threads, you actually get a speed up. At first, it looks almost linear, not ideal, but not far from it. And it goes, and it actually, this is the case for both shorter and longer runs. So fewer and more number of steps of evolution steps. The situation is a bit different for grid sizes. So if grid size is small, then you get comparable scaling with a time evolution. So again, up to over 20 times if your grid is okay. But then once the problem gets bigger on the single iteration time, OpenMP implementation, as you see, stops accelerating with number of threads, and it drops back to almost no speed up at all, maybe a couple or even less. And this can be explained. And the explanation is that for smaller grids, each OpenMP thread takes their own number of iterations and values needed to compute the updates of those iterations, and they all fit in inner caches of the respective CPU core, which means that everything can be done without access to the RAM, dynamic memory, which allows for almost theoretical scaling. Once the grid or the portion of the grid assigned to a thread becomes too large, and it has to be read and written back to the RAM for each iteration, then the speed up breaks down. At this point, to check what should happen and what happens when increasing time steps and grid sizes, one is invited to think about the algorithmic complexity of their particular problem. So in this case, I have time evolution of some two-dimensional grid. So the question is how it is expected to scale with respect to the number of time steps. So if I increase the time steps, how will the computation time increase? And how that computation time is expected to increase with the size of grid side. The answers are just behind the spoiler tag, and also the optimal question for you to look up is, do you expect that your GPU accelerated computation will follow the trends that you estimate? If yes, why? If not, why? I won't dwell too much at this, just show the answers. So I expect the computation scale linearly in time, because each time step is computed independently, one after another. And I would expect theoretically the computation time to scale quadratically with grid side, because I have two-dimensional grid. That means I have n squared points to update, where each update is more or less independent and on the same computational cost. Okay, so this is CPU implementation. For small grids, it looks very nice. For larger grid, it looks not so nice. What can we do first to port this code to GPU to make it run on the GPU with minimal effort? And then can we do some optimizations or apply some principles you've heard in this workshop to make it actually run efficiently? So for that, let's consider two possible minimal implementations, so OpenMP directives and SYCL implementation. With OpenMP, you may have still remember from the first day, with OpenMP you can offload your code on the GPUs, basically by using keywords target teams distribute. And then if you also want to make sure that your data gets mapped from the CPU RAM to the GPU RAM correctly, you can add mapping directives as a second line of the pragma. With SYCL, which is basically a type of kernel-based programming, CUDA example would look quite similar. What you have with SYCL, you can check that the loop actually disappears. But of course, instead of a loop, you get literally the same code to be run as multiple kernel functions on your GPUs. And then those kernel functions can be defined almost identically to the inner loop of the previous C++ program, with some things to be able to encapsulate them and put them by the way SYCL does it. So for that, the object called Q is used here. So now I've already compiled the OpenMP based executables, actually both CPU and GPU versions, and I'm trying to compare them to SYCL ones. So SYCL code is in the other subdirectory of the lesson material and the SYCL subdirectory. And to be able to compile and run those, you also need to add some other modules if you're doing that on Lumi. So if you already have the allocation, you don't need to reallocate it. Let's change the models and let's try to compile and run the SYCL-based executable. I'm moving to the SYCL subdirectory. I'm reloading. Actually, most of the modules are the same, but just to be sure that everything works for you as well for me. I have reloaded the modules. And I will try to compile those. The compilation takes slightly more time than the C++ version, but I think a minute should do it. So the first one is done. The second one. In the meantime, to check what the situation is with the resources, maybe please give thumbs up if you're able to follow this on Lumi. So looking up for the afternoon session as well. If you're able to log in, if you're there. Meanwhile, the compilation is done, and I have two new executables, one called stencil naive, the other called stencil. Similarly to the previous examples, I can run them on the compute node by employing a srun keyword. Good. So the source code is actually written in a way that when you compile the executables, you can actually test them with different timings and grid sizes. So before now, I was using just the reference run. But I can do things like that. Something like srun stencil, grid side X, grid side Y, and time steps. So there. So this is actually the default grid side of 2000 and 500 time steps. You can check that the output result, so the average temperature, is the same. One could also look at the grid of values after the last iteration, and there is a possibility actually to generate images on some time points for that. For the purposes of simplicity, it's disabled at the moment, but you can always turn it on. Okay, so you might actually play around for a few minutes and see what happens if you change time steps and grid sizes. And again, in base folder, stencil is the CPU accelerated one, so probably the one that you might already have, depending on your particular problem. And stencil off and stencil data are two versions of GPU accelerated OpenMP computations, while stencil naive and stencil in SYCL subdirectory are the two examples of SYCL-based implementation that both run on the GPU. You can run and check what happens to make some estimated guesses of what should happen and why. I will now go over our first tries. So again, as I mentioned, these are the first two port source code on the GPU to make sure that it works, and then to see if there are things that one can optimize. So OpenMP and SYCL. And also one can compare this with either full CPU parallelized implementation, or maybe just running code on the single CPU thread, because for many of us, this may be the first version that one actually codes and tries out. Does it work on a single CPU? And so, if you will do that, or if you will check the graphs here, you can notice two things. One thing is good, the other thing is to be improved. So the good thing is that in all three cases, sequential operation, OpenMP implementation by adding one line to the pragma, and SYCL implementation by implementing SYCL Q and putting your inner loop code as a kernel into that. They all work theoretically correctly. So they scale linearly in terms of computation steps, and they scale more or less quadratically in terms of grid side, or you would say linearly in number of elements you have to update. The only difference is in these graphs is on the Y scale, Y-axis. And there is the improvable thing. So this is a sequential stencil computation on a single CPU core. And both naive implementations, both simplest implementations that run on GPU, and they do run on GPU, they are actually slightly slower than the sequential one single CPU core version. As you see, this takes up to 25 seconds for 8,000 grid and 500 steps. This takes 50 seconds, while this takes 30 seconds in a bit. So on the one hand, it's good. GPU porting is complete. On the other hand, it's not good because you haven't justified why you needed all the time to do the porting. Luckily, in some cases, that all the time was finding a single line, the pragma. But, well, study of the material also does take time. So I'm not diminishing that. Okay, so what is one thing that is definitely needs to be done for the code to run more efficient? And it has to do with the structure of the source code. So this is an update. This is also an update of a single grid from one step to another, one time step to another. And in both cases, here and here, here it is implicitly. Here it's written explicitly. But what you can see is that the copying of the data, so grid values from the CPU to the GPU memory, is done at every iteration, every timestamp. So at every timestamp, the data is copied into the GPU and back after the computation. Because while this is a nice way to map your data, it persists only until the end of the block that this pragmatist directive is covering, and this is actually before the end of the eval function. What does that mean? That means that there is a lot of unnecessarily data movement from CPU to GPU and back from GPU to CPU on each time step, while in many cases what one wants to achieve by solving the differential equation to evolve their solution is to get some snapshots of that solution in forward time. So somewhere along the way, maybe after 500 iterations, maybe each 500th iteration or so. And actually, the results of each time step are being reused to compute next time step, which means that it is completely unnecessary to delete the data from the GPU memory. So we have to find a way to keep that in the GPU memory. And this then is done by allocating GPU memory once, copying data, initial data once, and copying it out only when it's needed for you, for example, to see some intermediate snapshots. Otherwise, all the data manipulation can be done in GPU memory without notifying the CPU part about that. So these are the versions of the executables: stencil data in base subdirectory and stencil in SYCL subdirectory that implement that. So in OpenMP case, this is leaving the directive actually simpler, but then doing manual data entry and update, as has been told in the previous episode on the directive-based GPU programming. So you have a couple of new functions: enter data, exit data, and update host, which by the names should be self-understandable, and they are actually used in places where it's needed. Otherwise, the data to update actually stays on the GPU memory. You can do similar things: copy to buffer and copy from buffer in SYCL. And again, to go a bit ahead of myself, one can actually implement this in Python using a syntax similar to CUDA by using numba JIT compiler, and their data movement functions are actually already given to you for free by the numba CUDA implementation. Okay, but for the moment, I'm staying on C++. And let's look how it works. You may have noticed one thing in my test runs, and that thing was a SYCL run. That looks like a nice time. 500ths of a second. That does look nice because I can increase the problem size, at least in one dimension, so in time, 100 times, and still be able to show it without much delay to you as an example. So let's go through the solutions of what happens if I'm using explicit data management in both OpenMP and SYCL implementations of the heat equation or stencil computation porting. So first, on the OpenMP, so data map OpenMP performs much better than the initial version where the data was copied every time. And as you can see, it actually outperforms even fully CPU parallelized OpenMP version on any larger grid sizes. So grid sizes larger than 4,000 or 5,000 per site. So once you get to the memory that is too large to fit in the CPU caches, you can't get CPU optimizations on there. And then copying memory is worse than not copying memory, or reading data from slow memory is worse than reading data from fast memory. And these are the summary graphs of the implementations I've shown so far. So you can see there are 6 versions. The blue one is CPU parallelized version, or let's say the reference version. Then there are single thread version, first attempts at OpenMP GPU porting and SYCL, and then updated attempts at OpenMP GPU porting and SYCL. And you can look at the scaling behavior, both in increasing time steps and increasing grid size. In time steps, very nicely everything scales as it should, so more or less linearly with number of time steps. And proper GPU implementation, so based on CUDA or SYCL or maybe even OpenMP, if you can tweak some values, this is still to be seen, then you can get comparable behavior on the single GPU and a single CPU node. Of course, this equivalence may be a bit accidental, but in a way, the technology evolves in parallel, simultaneously. So good CPU node and good GPU node is more or less at least comparable in what it can do in number of computations. So you see this is 4 small grids in time, while for increasing grid size, you can now very clearly see where OpenMP stops benefiting from CPU optimizations and then goes out just to be a RAM-bounded version, where actually GPU parallelized OpenMP version behaves much better. But due to the fact that OpenMP did most of the work for ourselves, so one told via directives which part of code to put on the GPU, but not necessarily how exactly to do so. There were no explicit thread sizes, block sizes, and things like that. Those can still be played with, but even without that, GPU parallel versions for larger grids of computations now are the 2 best versions. And lower level is about an order of magnitude faster than the higher level. Now I will take a couple of minutes to look at the HackMD if there are any questions related to the C++ part. There is one question, but I think it's already being answered. So what to do if your OpenMP parallelization starts becoming RAM-bound? And the answer is, well, chunk it into smaller pieces. Again, one thing to look for is, for example, the reference version. What it does here, the pragma, it actually parallelizes only over one dimension. You can try parallelize over both for loops. So parallelize not over lines, but maybe over some chunks of iterations. Of course, then you have to start thinking about your memory access patterns, but this may be the way, or one of the ways. Because what happens here is when a single line or a chunk of lines gets too large to fit in a CPU cache, well, then this is where all the RAM reading starts, reading and writing back. Okay. And then there is an increasing number of researchers that would like to try out their problems, implement them and put them on the GPU, not by using the popular HPC languages as C++ or Fortran, but the languages that are popular at general programming in recent years, such as Python or Julian. So I did mention on the first day that with Python you might have multiple choices. One of the choices is to write all your template and administrative code in Python and then call some C optimized program or Fortran optimized program, or you can do even more within Python and then go back to low level programming only when absolutely necessary, or actually do that low level programming directly in Python. So one of the nice libraries that is available but only for CUDA as of this moment is Numba, because in Numba you can try to write your code and then parallelize it both on CPU and GPU by using different syntaxes. If you do know CUDA, this is probably the best, or at least the best in terms of efficiency. It is also possible to try and understand the GUFUNC or UFUNC syntax. So as Numba CUDA will not run on the Lumi, you can still try out your examples on Lumi, maybe with the newer Python version than written here, or maybe this one is still available. You can try the JIT accelerated versions without GPU support directly on Lumi. If you want GPU support, you might try that on your own GPU resources, or the other option is to go to cloud. And Google Colab is one of possible choices to do so. So I will run the Python JIT accelerated examples as a Google Colab notebooks, just to show the similarities and differences. So this is equivalent Python code for evolution. This is generic code, and JIT can actually compile it to run efficiently on CPUs. CUDA, Numba CUDA, or CUDA JIT would be able to do so, or to do so with some changes on CUDA capable GPUs as well. And actually, as you may have noticed, I already have shown the differences between the reference implementation and CUDA implementation in Python here in the earlier tab. The kernel function actually looks more or less identical because, again, there is one expression. This expression takes most of the computation time. You want to run this expression either on your CPUs or GPUs. And then you have to do that in different programming languages or different programming frameworks. And depending on which language and framework you choose, you might have to do some additional writing. So If you use CUDA through Python, then you still have to know of concepts like blocks and threads, and then put necessary values in there. Okay, so how does it look? The code is provided as, again, separate files that could be run in command line. Well, any Python implementation, Python distribution. If you want to run them in Colab, you have to put them in Notebook and maybe get rid of differences, inclusions between files, but otherwise the code remains more or less identical. Okay, and first I'm going to run the Python variant that is accelerated by JET, but not yet accelerated on the GPU. Accelerated generation function and accelerated evolution function. This is accelerated by using just-in-time compiler, but not yet put on the GPU resources. And then you can change the values, for example, here, and see how it does. If you remember the comparisons from the C++ versions on the Lumi node, you might remember that some of them were of comparable time, while the others were much, much faster. Also take into account that this is being run on a relatively weak hardware compared to the Lumi node. Okay. It does look okay as scaling with time. And I can check the scaling in space with grid size, with respect to grid size as well. So 3 seconds divided by 4, or gave me something in the order of 12, 13 seconds. Not too bad. Okay, what do I gain if I use GPUs? As Google Colab allows me to use only one active allocation at a time, so I had to remove the previous one. Okay. Okay. So there's the main difference. Instead of JET, that is CUDA.JET. And the kernel is probably almost the same. There's some additional code to define what needs to be told to the CUDA hardware to be able to place the kernels efficiently. Okay. I will run this a second time just to be sure. Okay, I get it under a second. And actually, you can check out what hardware you have, even from the Colab interface. So if you use NVIDIA SMI's, let's say, keyword to run, you can check out what you have. You have Tesla T4. And then in this case, it runs twice faster. So not too exciting, but still it does some job. And in Colab, I can also look up, at least for a glance, at the resource usage here in the resource tab. We can clearly see that GPU was loaded for a time that it took the Python version to compute the 8,000 side grid. I can repeat that with even larger grid. Look at what happens, if anything. So of course you have memory usage on the system RAM because Python does store the data in the system memory. Then when it's time to compute it, CUDA also copies it to the GPU RAM as well. Unfortunately, straight from the Colab notebook, it's not possible to run two cells at the same time, but there are actually workarounds. There are ways to track the usage of the GPU resources during your Python program runs as well. In the meantime, has anyone tried to do that in Julia? To try out the Julia examples? If you did, you can tell in the HMD how that worked out for you. Meanwhile, as the closing words for this, I will tell that this is actually this is a example adapted from some efforts of other people all over the years. There is a similar implementation of heat equation on CSC, which is implemented in many languages and frameworks. Not necessarily related to the GPU. So, for example, MPI. and even MPI were CUDA.